Hello, good morning to Doctor. So today I'm going to present for the part two where perform the mass and energy calculation by using computer-aided balance approach. So basically I'm going to use the COCO open software simulation. So basically, firstly we need to go to the setting in this whereby we will set the property packages, reaction packages also. So firstly, click the property packages, then add, and then click B. And then this is all the item already in the setting, but we're going to use our own item, so we're going to click new. Then for the name, I'm going to put methane. The name is it can be put anything. So next, the model set that I'm going to choose is Peng Robinson because it will be easier to be calculated. And then the next, I'm going to add all the component in this direction. So the component that I use is methane, and then I'm going to add also ethane, and then carbon dioxide, oxygen, water, and last is nitrogen. Okay, then we said okay, and then assign the property packages to the default syntax. And then the next one will be going to set for the reaction packages. So add a new one. This one we're going to click on reaction package manager, then set also a new one. And click the new reaction package. The name also put as a methane, same as the one in the property packages. And then for the compound, I'm going to add all from the property packages also. And then just click all of it. And then because I have a reaction in it, so I'm going to put my stoichiometry. So I'm going to click for reaction one. And I also got my second reaction here, so I'm going to add it. So for the first reaction, it's going to be methane. So methane will be reduced because it is the reaction, so going to be used up. So -1, and then oxygen also going to be used up. So -2, and then carbon dioxide going to be increased by 1 only, and then for the water it's going to increase by 2, and then I'm going to put it as heterogeneous, and then the heat of reaction, this one is I already calculated it based on the uh, table of property, which is the one that I got is 929980, because I already changed it to joule per mole. and then the phase is going to be liquid. Okay, the next one will be proceed to reaction 2, and then for reaction 2, ethane going to be -1, oxygen going to be -7/2, equivalent to 3.5, and then the carbon dioxide that produces 2, then the water that produces 3. So also heterogeneous, and the heat or reaction is also obtained from the table property, and I got 1683320 joule per mole, and then the phase will be going to be liquid, and then put OK, and then for the setting it's all done. So now we go back to the flow sheet. Firstly, include the insert stream. So for my part, it's going to be a bit different from the question because some of the unit operation is not available. So firstly, for the I'm going to change the pressure into ATM, and then going to be 1 ATM. The temperature I'm going to use Celsius, and the temperature is going to be 245. Because of the uh, some unit operation is not available, I'm going to include some of the component in one stream. So next I'm going to proceed with compound flow. So for the first compound, I got like oxygen. My oxygen level or my oxygen compound is 248.90 mole per second. Then my nitrogen is 936.34, and then I got methane, which is 95, and then ethane 25. So this is my, and then it's the overall properties already being calculated. So this is my enthalpy and enthalpy of formation, and I also got the mole fraction for methane, ethane, oxygen, and nitrogen. Then I'm going to run this stream, and when it's turned to game, that means there is no problem for the stream. So I'm going to finish it very quickly. So first I'm going to insert unit operation, which is I'm going to include reactor because for the furnace I can't find it in here. So I'm going to fix conversion because there's a conversion in this, and then I will assign the reaction package, make it big so that it will be much more clear. So basically, first assign reaction package with this methane, so and then connect the stream to the unit operation, and then click again to this one, and then edit it. So so I'm going to assume for the temperature, because the in outlet stream is going to be 900 degrees Celsius. So I'm going to change it to Kelvin. 900 plus 273.15 equal to 1173.15. And then because I have reaction, I'm going to add my reaction. Reaction ID, the first reaction, and the conversion is 1. And then compound that I'm going to take is methane. And then add again for reaction 2, conversion of a 1, and then of compound ethane. So then put K and then X, and then also X. Basically, I'm going to put the insert another stream. This is the outlet stream. So and then I have a preheater, which is the uh, stack gas is going to be reduced in temperature. That's why I'm going to use unit operation where heater cooler. So I'm going to put it here. I'm going to make it big. I cannot be big. So and then insert the stream here, and then also insert the outlet stream. Also, the stream, the pressure is going to be 1.2 atm. Then the temperature is going to be in degrees Celsius or 900 degrees Celsius. And the compound flow, it doesn't contain methane and ethane. It contains carbon dioxide with 105 mole per second. Then we have water with 205. Then we have oxygen with 41.4. And then we have the nitrogen because it doesn't being used, so it will also stay the same with 936.34. So it's already being calculated, all the enthalpy, enthalpy F, and all the mole fraction. So next I'm going to run it. As you guys see, all will be turned to green. Only the fixed conversion reactor, there's some problem with it. And then, okay, next I'm going to proceed to the third or final stream. I'm going to name it as, stick to number, as the stack gas. And then the first one is going to be the air with natural gas. And then the second stream is going to be also stack gas. This one is also stack gas. Where it was going to be the final one. The difference is only in the temperature, so I'm going to set the temperature for the final stream where stack gas final. Double click it, and then the pressure also going to be 1.2 atm, and the temperature is going to be 792 degrees Celsius. And then for the carbon dioxide, oxygen, water, nitrogen compound, it's also still the same. And these are the enthalpy for it. And then X. And then I'm going to run it again. So basically, the problem can be solved. Okay. And then as you guys can see, these are the my flow sheet diagram for the fraction that I'm going to be using. So basically, there's a lot of differences because of the one that in the question uh, I need like two inlet and two outlet for the preheater, and then two inlet for the furnace and one outlet from the furnace. But because of I can find any furnace in this COCO simulation software, so I'm changing it to the reactor because since air is going to react with all the natural gas to produce carbon dioxide, water, oxygen, and also nitrogen. And then for the preheater, I'm going to choose heater cooler because there are change in the temperature before and after. That's all from the part of the flow sheet. And then as I have it here, for the stream one, uh, the enthalpy is going to be 6715.21 at 6. And then after it goes to the fixed conversion reactor, as it and out as a stack gas, the pressure is 1 atm with 900 degrees Celsius, and then the enthalpy is 29499.105. And then as it goes to the heater cooler, the enthalpy is remain the same, only the temperature has a big difference because it has been cooled to 792 degrees Celsius. So that's all for my part. Thank you.